Okay, so now we would like to present some real problems. When I say real, I mean problems of practical application that are appear often in logistics or in other fields. Okay, and can be mapped into a cube. And we will do an example with the maximum cut problem that is popularly known as the max cut problem. Okay, so what's the problem of max cut? So the idea is that we have a graph defined by a set of vertices and edges that connect these vertices. Okay, for instance, I draw a graph here. Okay, here's an example of a graph. So the problem is that we want to find a cut that cuts the maximum number of edges of this graph. In this case, would be this one. Notice that this cut cuts 4 edges, while if I just from this cut, I will cut one edge. Okay. So in this case, the solution of this max cut problem would be this set here. So if we want to formulate the problem more formally, we would say that in the set of vertices, we will decompose the set of vertices into a subset A and another, so the complementary set of A to A complementary that we define it in this way. Okay, so so A is a set of vertices, and a complementary is the set of all vertices that are in B but not in A. Okay, so basically the idea is that we want to find an A such that the number of edges that have one vertex in A and one vertex in A complementary is maximum. Okay, this is the formal definition. So this is the problem. So now we need to formulate, so the goal of this session is to formulate this problem as a QU problem. And for a QU problem, the first element that we need is the cost function. So we need a cost function, and we wonder what will be the cost function. And in this case, no, the cost function is, let's say, given a set of vertices A, so the cost function of A will be given as the following. No? It will be all the edges I, J, that fulfill the condition that one of the vertices belongs to A and the other vertex of the edge belongs to A complementary. So only these edges are taken into account, and we will just consider that they have a contribution 1. Notice that the cost function, I used the name cost function, but in this case, what we want to do is we want to maximize this cost function, since the problem is the maximum cut. We could have formulated the problem as the minimum cut, and then basically the goal in that case would be just to minimize the cost function. Okay. When we formulate this Q as a Q is also always formulated as a minimization problem. The one thing that we will do is we will put a minus sign in front of the cost function, such that the process as we do is a minimization instead of a maximization. Okay. So now we have the problem properly formulated in terms of subset K. Okay. But in a Q, the conversion space of a Q is not are not sets, but are binary strings. So the first thing that we need to do in order to write this as a Q problem is to find an encoding. We need to find an encoding from the power set of so the power set is the set of all sets in, or the set of all subsets of T. Okay. We want to go, to the set of bit strings of length n, where of course n is the number m here is the number of vertices that we have. Okay, so in this case it would be 5. So the simplest encoding that we can find is the following. So we'll say that we will define it as follows. So given so x a bit string of length n, we'll say that if the vertex I belongs to the set A, then the ith element of this bit string, we will set it to 1. And otherwise, so if I doesn't belong to A, then we will set this bit element to 0. Okay, so this function encodes any subset of B that you can think of into a bit string, and you see clearly that it's a bijective application. So also any bit string has corresponds to a subset of bit. Okay, so good. So we have a cost function expressed in terms of the subset A. We have an encoding from the power set, so the set of all the subsets of B into the bit strings. And the last thing that we need in order to have the formulation of the max cut problem as a cubo is rewriting the cost function instead of in terms of subsets, no? Because function of a subset A is given by this function. So we have to written this cost function in terms of the bit strings X. And in such a way, we will be able to formulate our max cut problem as a cubo problem. Okay, so the goal is that we would like to change the cost function expressed in terms of a function that depends on the subset A as a function that depends on the bit string X, where X, X is a way of encoding the subset A. And notice that we would like to have an expression of this type where this function f of xi, so basically takes, let's say this takes value 1 if let's say if I belongs to A and J belongs to A complementary, okay, or the other way around. Good. And we want that takes the value 0 otherwise. So if I belongs to I and J, both I and J belong to A, or I and J belong to A complementary. Okay. So notice that there is a very simple function that will have this property, right? Because we know that if I and J belong to A, it will mean that both will, xi and xj will have value 1 for both. If I and j belong to A complementary, both will have value 0. But in contrast, if I belongs to A and J belongs to A complementary, or the other way around, the difference will be always positive. So notice that one way to solve, to derive this function, is that this function here it could be, for instance, the absolute value of xi minus xj. Or as we are dealing with a QO problem, it would be even easier if we just take the square of this function. So this function fulfills these properties. So basically what we do is that we just replace this function here by this square of the difference. That, of course, we can write it as xi squared plus xj squared plus, minus minus 2xj. As xi and xj are binary variables, its squares the same as are themselves. And then basically we can formulate the problem as xi plus xj minus 2xi times xj. Okay, again, this is the cost function, but we want to maximize this function. As in Q, in the Q of formulation, what we want is we want to minimize it. So we just add a global minus sign in front. And therefore, we have the problem formulated as a Q problem. So now we have a particular graph. We have an example, but we will have a particular graph. We see that all the terms that we will have will be of the Q type. And then it's easy to write the Q matrix of the Q from this expression. We will do an example right now. So let's try to do an example of how this Q formulation of the max cut works. So imagine that we have a graph like this one, and we want to write the cost function. So basically, the only one thing that we need to do is just to follow which are the edges of the system, right? So notice that in this graph, not all the vertices are connected with the vertices, and then we will have to just follow the edge set. So we'll get a term of this for every edge, and with this we will write the cost function. So let's do this example. So for this graph here, the cost function will be, we have an edge between vertex 1 and 2, so this would be minus x1 minus x2 plus 2x1 times x2. Okay, this is the first term in this sum, where I just have applied this minus sign was globally here inside these parentheses. Okay, then we go to another page. For instance, I know the h13, and then we would add another term that would be minus x1 minus x3 plus twice x1 times x3. Okay, and then we do another edge. So this is done, another edge. So minus x2 minus x4 minus plus twice x1 times x4. And we will do this for all the edges. Okay, for all the edges. And at the end, the only one thing that we'll have to do is just to group terms. Okay, when we group terms, we notice that we'll have two types of terms. Sometimes that will be let's say linear if you want, it will not be quadratic. Quadratic in the sense that x1 is equal to x1 squared, okay, but will lie in the diagonal of the Q matrix. So all these coefficients will add in the diagonal of the Q matrix that we read right now. And then these terms in here, basically, they correspond to these edges. So basically, we will have off diagonal elements. No, the row 1 column. So this will collect this will be a number in the positions row 1 and column 2 of the Q matrix. Now, so I don't continue because I think it will be very long calculation, but I will write now directly the Q matrix that we obtain after doing this. So here I have written the Q matrix associated to this cost function. And notice that although the cost function was very long, the Q matrix is relatively simple because what we notice that, for instance, the diagonal elements correspond to these elements that we have here and that are alone. And then what we see is that precisely they have always a minus sign and the degree of the vertex of the graph. For instance, the degree of the first vertex is 2. It has 2 edges adjacent to it. So it has the degree 2, and then its corresponding terms of -2. And the same happens with the other side. Vertex number 4, it has degree 3, so it should have a diagonal element in the Q matrix that is -3, and indeed it's -3, and so on and so forth. The rest of the elements are always 1, because although here it appears global factor 2, this 2 can be composed in x1 times x2 plus x2 times x1. And then we just decompose x2 in these 2 contributions. And this x1 times x2 would be just this element here and this element here, that would be at them, they give 2. Okay, so at the end, in practice, we can, in the formulations of the max cut as a cubo, it's not necessary that we go through the, let's say, the polynomial of the cost function expression, but we can write directly the Q matrix with these 2 easy rules, that the generality correspond with a minus sign to the diagonal elements, and the connectivity of the graph is encoded, so that the adjacency matrix of the graph is encoded in the off-diagonal elements. So with this example, we have seen how a max cut problem can be coded into a cubo in a very natural way, and the problem is particularly simple because there were no constraints. Okay? There were no constraints because in the encoding, this connection was very natural, and every valid subset was corresponding any let's say, bit string. Okay. There are examples in which this is not so easy, and the encoding is not so natural, and then we need to restrict the space of all the binary strings with some restrictions, with some constraints. And this particularly happens in the travel assessment problem. That is a problem that we will explain now. So in the example of the max cut, we have seen that we can encode the problem into a cubo formulation without constraints. Okay. Now I would like to show you that in many practical problems, so the encoding doesn't make possible that all the candidates of solution have a meaning, let's say. And an example of this is the travel salesperson problem. Okay, the problem is very well known. So we have a graph that represents, so the vertices are cities, and the edges correspond to highways or to roads that connect these cities. And we have a function that tells us the distance between any 2 pair of cities in case that they are connected by an edge. So from this city U, we could go to B or to other cities, but we could go to this city up here. Okay? So this is the problem, the situation. And the problem is finding the shortest path that connects all the cities. There are several variations of the problem. So in some cases, you need to start and finish by the same city. In some other cases, you can start by the vertex that you want and finish with the vertex that you want. But okay. So there are many encodings of this problem. And none of these encodings, you have to impose some restrictions. To me, one of the simplest encodings of the problem is the so-called one-hot encoding. That basically, so this is binary string. Notice that this binary string doesn't have, so let's assume that the number of cities is n. So n is the number of cities that we have. And then, okay, so then what we notice is that the way in which this encoding works is that at time 1, we start from city 1, and then at time 2, we go from city 1 to city 3, and so on and so forth. Okay, basically, it's a binary string where the information is encoded in this way. No? At every time, we express without 1 the city in which we are at that time. Okay, it's easier to represent this in terms of a matrix, but this doesn't matter because this matrix can be flattened afterwards. So this will be at the end of the day a bit string whose length will be n squared. So the encoding is not very efficient, and unlike the mascot, in which the encoding a problem of size n was encoded in a solution of size n, here is n squared. Okay, because we have to specify time and place for every time. Okay. The cost function can be written in this way, where we see that two cities that are visited consecutively take a value 1, and then this factor is 1, and then we contribute for that distance. And then if one of the two cities are not present, so I imagine that one path goes from U to V and doesn't go to this city here. So then the city will take a value 0 and it will not have contribution in this sum. Okay, so this is the cost function. But of course, this cost function is not good because it would allow, for instance, that if we don't put any constraints, as all these quantities are positive, because these are distances that are positive, no? The minimum value of this function would be just put zeros everywhere. Okay, so we need here to specify some constraints that ensure that, okay, that I'm somewhere in every instance of time, and that I go from one city to another one. Okay, so just as an example of the type of constraints that we will have, it means that for every t, we would like to be somewhere. That is that with the sum of all the cities at this given t, it needs to be 1. Remember that these coefficients are bits, so this is a binary string. So the only one way to guarantee this is that at least one of the use doesn't takes the value 1. Okay. The same thing we could say for the constraint that at least one city needs to be visited at some time. So it's not possible that a city is not visited for all times. So this can be imposed with the following constraint. So for every city, for every U, we need that the sum over all T, that is U T, is also equal to 1. And so at least every column we need to have a 1. Okay, and the goal of this example is just to show that the cost function can be modified to include these constraints as follows. So basically, the cost function that will allow for a Cubo formulation of the trouble Salesperson problem, it would be the cost function original that we had, that doesn't take into account the constraints, and where we have to add 2 penalization terms, right? One penalization term, actually it's not true, it's n penalization terms in order to impose this condition here, plus n penalization terms to impose this other condition here. So let's write it in this way. So these conditions are imposed for all t, where for each of these t, we need to impose the following. Okay, so these are end conditions corresponding to the fact that we need to be at any time somewhere. Okay, and then the other condition is imposed as follows: is that any city needs to be visited at some point. Okay, so with this we show an example of how the Talos S1 problem can be encoded as a queue, and we wanted to emphasize how we impose constraints in some problems, such that in this case, notice that not all the binary strings were possible configuration, a real configuration, but just the real configurations had to fulfill certain conditions. Okay, so with this, we finished this lecture where we wanted to show the use, the encoding of, we wanted to show how real and practical problems can be mapped into a QuTalent formulation.